Hello, AP Calc BC. This is Chapter 10, Topic 4. We're doing displacement and distance traveled, polar coordinates, polar curves, and slopes of polar curves. So, by the end of this, you should be able to use vectors to calculate the displacement and distance traveled of an object moving in a coordinate plane. Excuse me. You should be able to use polar coordinates to define curves that would be difficult or impossible to find with our typical functions of y as f of x. And you should be able to convert polar coordinates to rectangular coordinates and identify the shapes of polar curves. So this kind of ties together a lot of the different topics that we've been doing in Chapter 10 between the parametrics and the vectors. With polars, you can think about them with two components, the x component and the y component, and typically we associate the x with cosine and then the y with sine, and we'll be using those to do some conversions from polar to Cartesian coordinates. And then the thing about polar coordinates is you can write them with a different parameter. You can use a third parameter, usually our angle of theta, and that can also show us how many revolutions we're making around something and how far we've traveled. Okay, and then identifying the slope of polar curves, that's just a simple calculus application of all of this. So the first thing that we want to remember is what we already know about calculating displacement and distance traveled. So if you remember that when a particle is moving along a line with its velocity function, the displacement or the net distance traveled between your initial time and your final time is given by the integral of your velocity function. And then the total distance traveled is the absolute value of that integral. So when you have a particle that moves in the plane with your velocity vector, the displacement and the distance traveled, you can find that by applying those same vectors or those same integrals to the vector v, but just a little differently. Okay, so we can still do this with vectors and we can still use integrals. We just have a few small things to go over. So if we talk about displacement and distance traveled, so let's consider this particle moving along a path with a velocity that is given by the vector with two components, v sub 1 and v sub 2. And both of these components are integrable functions of t. The displacement from the initial time to the final time is going to be given by this vector here, which is, so the first component is the integral of your first component from your velocity function, and then your second component is just the integral of the second component of the velocity function. So that makes sense. We know displacement is the integral of our velocity function, so that would make sense that our displacement vector is the integral of those components. Now, what we can do, if we take this vector and add it to what we know about our initial position, that will give us our final position. Okay, and we'll actually do that in example 1. And then distance traveled, so that's something that's different from displacement. Distance traveled is going to be the absolute value of the vector, the absolute value of the integral of the vector. And so you can do that, or you can apply your, well, I guess how you would do this is this right here, which is finding the magnitude and then taking the integral of it. And this is the same thing as our arc length formula. And that makes sense that it's the same thing as our arc length formula, because if you think about the distance that a particle travels, you're just measuring the length of its path, right? Which is the same thing as arc length, okay? And that's exactly what the next slide covers, is the relationship between these formulas for distance traveled and arc length, and they're pretty much the same thing. And so because if we think about velocity as our derivative of the x component of the position, and the second component of velocity as the derivative of the y component of position, and we throw those in here, then that's the same thing as our arc length. Okay, so we have that nice connection there. Alright, so with example 1, we have a particle moving in the plane with velocity vector t minus 3 pi cosine pi t and then 2t minus pi sine pi t, and its initial position is 1, 5. So what we want to do is find the position of the particle at t equals 4, and then the total distance that the particle travels from 0 to 4. Okay? So, with this, what we can do Alright, so if we start off, we want to find our displacement. Okay, so that's going to be, we'll take the integral from 0 to 4 of our first component, t minus 3 pi cosine pi t dt, and then the integral of our second component from 0 to 4, 2t minus pi sine pi t dt, right? And so if we take those antiderivatives, we're going to get t squared over 2 minus 3 sine pi t evaluated from 0 to 4, and then t squared plus cosine pi t evaluated also from 0 to 4, right? And so then if we evaluate those antiderivatives and simplify, we're going to end up with 8, 16 as our two components. So then, but we still have to do a little work to find the final position. So what we would do, our next step would be to add the points we have for our initial position. And so we would say the particle is at the point, we're going to do 8 plus 1, 16 plus 5, which is going to give us 9, 21, right? So 1 and 5 are just the coordinates of the initial point, or the initial position. And so then we can add those to get our final point, or our final position. Alright, so then for part B, we have to find the total distance traveled. So this is going to be the integral from 0 to 4 of the absolute value of our velocity function evaluated with respect to t. Right, so we'll have the integral from 0 to 4 of, okay, so let's see, t minus 3 pi cosine pi t, the whole thing squared, plus 2t minus pi sine pi t, the whole thing squared, dt. That's a nice mess, so I'm just going to plug that in my calculator and mint it, and I'm going to get about 33.533 units, and that would be the distance traveled by the particle. Okay, so that's it for part B. So the next thing we can talk about, example 2, we want to determine the path that the particle in example 1 travels going from 1,5 to 9,21. So this is definitely a graphing calculator problem, and if you were to have something like this on the AP exam, it would probably be multiple choice. It would probably be in the calculator section. Maybe they would give you a really simple one in the non-calculator section, and they'd give you a real simple example, and then your multiple choice options would be pictures of graphs, and you would have to pick whichever one matched the path of the particle. And it would probably be, if they did it in the non-calculator portion, it would be something that was, an easy shape to pick out. This one is kind of weird, so maybe they would put this in the calculator portion, because you definitely have to plug it in. So we've got to do a little work, though, before we plug this into our calculator. So we know from what we were given and what we figured out in the previous problem, our velocity vector is t minus 3 pi cosine pi t, and then 2t minus pi sine pi t. Okay? Now, our position function, so s of t, our position vector, is the antiderivative of that. So t squared over 2 minus 3 sine pi t plus c, and then t squared plus cosine pi t plus c. Okay? Now, we know that at t equals 0, our xy point is 1, 5, right? So we know at t equals 0, this whole piece right here equals 1, and this whole piece right here equals 5. Okay? And so what we have to do is we would plug 0 in for t to figure out what c is, plug 0 in here for t, and figure out what c is. And so if we plug 0 in for t here, well, the whole thing goes to 0, and then we're left with, so you have a 0 minus 0 plus c. So then for your first component, c is 1. And then for the next piece, if we plug 0 into this, we would get 0 plus 1 plus c. So then for this piece, c is 4. Okay? So then we can get our x and y functions here. So then x is going to be t squared over 2 minus 3 sine pi t plus 1. And then y is going to be t squared plus cosine pi t plus 4. Okay? So then we would graph parametrically with the calculator for t equals 0 to t equals 4. Okay? Now, when you plug this into the calculator and you use the parametric grapher, you've got some options for what you plug into your window for the x and the y. So we kind of want to think about, well, what would the domain of x be here, and what would our range of y be? And so just based on, the max and min values that you could have in the interval that you're working with here, we're going to say that for our x window, let's do -5 to 15. And then for our y window, we'll do 0 to 23, right? And so then and so where am I getting these numbers from? Well, if we think about t is going to go from, the interval of t is from 0 to 4. So you kind of, 0, the smallest value there would be 0, and then what would 4 give us? And then the same thing for y, what's your max and your min going from 0 to 4. And so that's how I get these values for the window. So if we go ahead and plug those things in, then put them in our calculator, and we would get a graph that looks like this, right? And so you can see it's definitely a weird shape. So this would be something that they would have on the calculator portion of the exam. It'd probably be multiple choice, and maybe this would be one of the multiple choice options for the graphs, and you'd have 3 others, and you'd have to pick one that correctly modeled the function that they gave. Okay? So let's go on to polar coordinates. So polar coordinates, well, first off, what we want to say is that what you guys have worked with so far this year is rectangular coordinates, which you've known since pretty much second grade, and those are just x, y, and then parametrics. And parametrics, you know, you've got three variables, you've got x and y, and then you can write x and y in terms of your third variable, t or theta or whatever you want to use. And then polar coordinates, they have two coordinates. The first one, r, is your radius or your distance from the origin, and then the second one, theta, that's your angle going up from your positive x-axis. Okay, so theta is going to be, so r is your directed distance from the origin, and then theta is the directed angle from this positive x-axis. And so it's important that we think about this as the positive x-axis. Okay, so the example that we have right here is the point 2, 2, right? And so if you plot this on a graph, you know that we make a perfect square, and then you could take the square and divide it in half, and then you have two right isosceles triangles. So then you're pretty familiar with this point and the features all around it. And if we were to draw a line out to it, and you know that angle that we would form would be 45 degrees, or pi over 4, and the distance of the diagonal of this square is 2 root 2, right? And you can also use the Pythagorean theorem to figure that out. So the polar coordinates of this point 2, 2, are 2 root 2 and pi over 4. So these two things, these two sets of coordinates are equal to each other, and you can go back and forth between the two. You can convert from rectangular to polar, and you can go back from polar to rectangular. Okay? So, how do we do that? Well, one of the things that we want to say about this before we go ahead and do this is that any point in the plane can have an infinite number of polar ordered pairs. So maybe we should backtrack a second and just talk about rectangular coordinates. If we look back at this drawing or this graph that I just showed you, this point 2, 2, this point P right here, it can only have one set of coordinates, 2, 2. That's it. There's no other way that you can write this point in the rectangular or the Cartesian form. But if we switch over to polar form, there is an infinite amount of ways that we can write our coordinates for this same point. So we could have 2 root 2, pi over 4, or what we could do is we could go around the circle and we could add 2 pi to it, and then we would have 2 root 2, 9 pi over 4, and we could go around the circle again, and we could have 2 root 2, 17 pi over 4, and we could keep doing that forever and ever and ever, and we could also go the opposite direction, and then we would get a negative angle. So you can have, there are infinite ways to write this same exact point, okay? And so that's what we're showing, or that's what we're talking about on this slide here. Now, the other thing that we want to talk about is the directed negative distance, okay? If you have the point 2, 2 right here at the tip of this arrow, it's pretty easy to tell that the distance from the origin to that is is 2 root 2. And so we call that our directed positive distance because that is the shortest way right to that point. Now, if we were to flip it over, but we were still talking about this point, then that would be a negative 2 root 2, okay? Because we're going in the opposite direction to that point. So we've got a directed negative distance is negative 2 root 2, and then if we go that way, then our angle is negative, and it becomes negative 3 pi over 4, okay? So we can have positive and negative distances, but that's going to change our angle. And so we'll do some examples with that. So there are a few ways that you can convert between polar and rectangular coordinates. We've got a few equations that can help us. We have x is r cosine theta, y is r sine theta, and then r squared is x squared plus y squared, and then tan theta is y over x, right? And these are all things that can help us convert from one form to the next. Alright, so with example 3, you have two parts to this. So they give you some polar coordinates, and you have to find the rectangular coordinates, and then they give you some rectangular coordinates, and you have to find two sets of polar coordinates for those. Okay, so now some of these are really easy to figure out, and you can just do them kind of visually by picturing where the point lies, and you don't even have to do any conversions. So for part A, let's see, so we'll start with Roman numeral I, and so that's the point 4 comma pi over 2. So this is one of those ones where you can just kind of picture where it is. Okay, so you know pi over 2 is the positive y-axis, and then 4 would just be 4 units up, and so the rectangular coordinate of that point would be 0 comma 4. And that was nice and quick and easy, and you don't even have to think twice about it. And then Roman numeral 2 is the same thing, negative 3 comma pi. Okay, well, for this one, so your radius is negative 3. Okay, so the negative, if your radius is negative 3, well, the negative distance, I'm going to start off with the pi. If my angle is pi, then that means that we would end up over here, right? Because this is pi over here. That's 180 degrees. But the thing is, our radius is negative 3. So because our angle is pi, and we're supposed to end up here, but our radius is negative 3, that means we're on the opposite side. So for this particular point, we are actually right here, okay? And so the Cartesian coordinates that would be this would be 3 comma 0, okay? And so the reason why we're over here has to do with that negative there. That switches your distance and reverses it from the angle that you're supposed to go. Alright, so let's take a look at number 3. Now, number 3 isn't as simple as the first two that we've done, so we'll have to do a little trig for this one. So we have 16 and 5 pi over 6, okay? And so, well, we can just kind of visualize where this is. 5 pi over 6 is about here, right? It's in the second quadrant, okay? And then we would be 16 units away from the origin. So for this problem, we know that r is 16 and theta is 5 pi over 6. So then we know that x is going to be 16 cosine 5 pi over 6, and you can simplify that to get negative 8 root 3, and then y is going to be 16 sine 5 pi over 6, and you can simplify that to get 8. Okay, and so where am I getting these relationships from? Well, just from what we were talking about a few minutes ago. Oh, it's actually on the other side of this paper. Just these relationships right here. X is r cosine theta, and y is r sine theta. That's where I'm getting those formulas from. Okay, so I have my x and y coordinates. So then the rectangular coordinates of this are going to be negative 8 root 3 comma 8. Alright, and then we can go on to Roman numeral 4, which is going to be negative root 2, and then negative pi over 4. Okay, so for this one, our radius is going to be negative root 2, and we know that theta is negative pi over 4. So then, and if we just picture where this is on the graph, well, let's see, negative pi over 4, that means we would be going in an angle in this direction, going down from our positive x-axis. Okay, so we would think that it would be right here, but our radius is negative root 2, so then that flips us to the other side, so we end up right there. Alright, so let's see. So we're going to say x, well, if that's r cosine theta, that's going to be negative root 2 cosine negative pi over 4, which equals negative 1, and then y is going to be negative root 2 sine negative pi over 4, which is 1. And so your coordinates are going to be negative 1, 1. And that's it. Okay, and it makes sense that it's negative 1, 1, right? Because that's where we land. Our x-coordinate is negative and our y-coordinate is positive. We're in the second quadrant. So that's it for example 3a. Let's take a look at example 3b. So for example 3b, we're given some rectangular coordinates and we have to find two different sets of polar coordinates. Okay, so let's see, for Roman numeral I, we have the point 1, 0. And so this is one of those that we could do this visually as well. So 1, 0 is just right here, right? And so for this point, my radius is going to be 1, and your theta could be 0. It could be a positive 2 pi. It could be a negative 2 pi. It could be negative pi, right? Because, well, actually, let's hold off on the negative pi. So you could have any of these points. So it could be 1, 0. It could be 1, 2 pi. It could be 1, negative 2 pi. So any of these would be fine. Now, and we also have the option to have a negative directed distance, okay? So a negative directed distance, well, when I do those, sometimes I like to think about the angle first. If I have a negative directed distance, that means that I'm ending up over here. So this angle over here, well, that's the angle pi. So if I go over there, but then I flip my distance so it's negative, I would have a negative 1. Or this could also be, if you add 2 pi to it, that could be 3 pi, right there, and then that would be a negative 1. Or if you want to go the negative angle to this, this is negative pi, right? So that's negative pi, and then you would still have a negative 1. So you only had to give 2 options, but here are lots of different ways that you could go, and you could keep going around the circle in either direction, positive or negative. Okay, and then for Roman numeral 2, we have the point negative 3, 3. Let's see, negative 3, 3, which is going to land us up here. Okay, so let's find our radius. Our radius is going to be the square root of 9 plus 9, which is root 18, which is going to be 3 root 2, okay? And then our theta, that's going to be, excuse me, the inverse tangent of y over x. So, inverse tangent of 3 over negative 3. So, that's going to give us, let's see, that's the inverse tangent of negative 1, which would be, that would end up being 3 pi over 4, right? And so that makes sense that it's 3 pi over 4 because it's halfway between. So then this could be your angle, and you could use 3 pi over 4, or you could add 2 pi to that, and let's see, that would be 11 pi over 4. Or if you wanted to go in the other direction, like if you wanted to start here at your positive x-axis and go this way, go clockwise to get there, that would be, let's see, that would be a negative 5 pi over 4, right? So you have a bunch of different options. So the points that we could make, we could have 3 root 2 comma 3 pi over 4. We could have 3 root 2 comma 11 pi over 4. Or you could have 3 root 2 comma negative 5 pi over 4. And if you wanted to use a negative radius, well, you would just flip your angle. So let's say, well, if I wanted to have this angle down here, this would be 7 pi over 4, right? And then if I reverse my distance back, that's going to give me my negative directed distance. That would be negative 3 root 2. So that's another option. Okay, so all of those are possibilities. And let's do Roman numeral 3. Okay, so for Roman numeral 3, we have 0, negative 4, and so this is one that we can just visualize. So 0, negative 4 would be down here. So that would be, you would have a radius of 4, and then that theta, well, that could be 3 pi over 2, or you could have, let's see, you could have 3 pi over 2, or you could have negative pi over 2 if you go in the other direction, or if you want to use your 3 pi over 2 and go around the circle again. So let's see, 3 pi over 2 plus 4 pi over 2, that would be 7 pi over 2. So some of the points that you could form with this, you could have 4 comma 3 pi over 2, or you could have 4 comma negative pi over 2, or you could have 4 comma 7 pi over 2, right? All possibilities. Okay, and then for Roman numeral IV, we have the point 1 comma square root of 3. So for this, our radius is just going to be the square root of 1 plus 3, which is going to give us 2. And then, let's see, the inverse tangent of, we'll do root 3, y divided by x, is going to give me pi over 3. Okay, so theta for this problem is going to be pi over 3, or if you wanted to add 2 to that, you could have 7 pi over 3. So some points that you could have could be 2 comma pi over 3, 2 comma 7 pi over 3, or if you wanted to do a negative distance, well, the opposite angle of pi over 3, you could have 4 pi over 3, and then the negative directed distance there would be negative 2. Okay, so these are all possible points, all possible polar points that could equal those rectangular points that were given. Alright, so in example 4, what you have to do is graph all of the points that satisfy these equations. Okay, so if you have all the points that have a radius of 2 away from the origin, right? So if the origin is here, and we have all these points that have a radius of 2, well, the obvious ones are the ones that are on the axis, and then you can fill in there, and you can see that all these points, they end up making a circle with radius 2. Okay, so the answer to this, right, is just going to be a circle with radius 2. And then this one is going to be the same thing. Because if your radius is -2, that just means a negative directed distance. But then if you do every single point with a negative directed distance, you're also going to get a circle. And then for this one, all of the points that have the angle of pi over 6, well, if you think about where pi over 6 is, right, well, this isn't drawn to scale, but it's something like this. It's 30 degrees. And if you think about all the points that have an angle of pi over 6, well, they all lie along this ray, and they go on forever and ever and ever in this direction. And then if you use a negative directed distance, they go on and on and on also in this distance. So we could say how we would describe this is just a straight line from the origin at the angle of pi over 6. Okay? And so that's example 4. So for example 5, for this one, you have to find an appropriate graphing window and produce a graph of the polar curve. Okay? I don't think you'll have problems like this on the AP exam, but it's a good skill to practice for graphing polar curves. So if we wanted to graph sine of 6 theta, well, you have to think to yourself, sine of 6 theta, the absolute value of that is always going to be between 0 and 1. Okay, so we want to have we want our graphing window to be at least from -1 to 1 on one dimension and -1 to 1 on the other dimension. But just to, I don't know if you ever knew this, your calculator screen has an aspect ratio of 3 to 2, right? It's not a perfect square, okay? The horizontal side is a little bit longer than the vertical side. So it has an aspect ratio of 3 to 2. So if we use a 1-to-1 scale, we have to think about that when we come up with our calculator window. So for, let's see, our X window, we'll do from -1.5 to 1.5, and then for our Y window, we'll go from -1 to 1, okay? And then we have to pick a range of theta. So theta will go from 0 to 2 pi. And then they'll ask us about our step, and we can use the same step for all of these. Our step will be 0.05. And that's a nice step because it gives you some detail without making it taking too long to graph and bogging your calculator down. So we'll keep this step for all of these examples, and we'll actually use the same range on theta for all of these examples. The reason why we can use the same range on theta for all of these examples is because all of our functions, sine and cosine, that is their typical range to get a full revolution, is from 0 to 2 pi. Now this next one, 1 minus 2 cosine theta, if you think about this function right here, the absolute value of 1 minus 2 cosine theta is always going to be between 0 and 3. Okay? So then for that, because of that, we could say, well, let's have our Y window go from -3 to 3, and then to match it with the aspect ratio, because it has an aspect ratio of 3 to 2, our X window will go from -4.5 to 4.5. Okay? And then for this next piece, 4 sine theta, so the absolute value of that is always going to be between 0 and 4. So then for our Y window there, we could go from -4 to 4, and then for our X window, we could go from -6 to 6, right? And then if you wanted to graph all of these are in this last slide here. these examples, these graphs, and you can see how our aspect ratio, you're going from, you've got 3 to 2, and how that affects things. But you can see how all of these graphs fit pretty nicely in the windows that we've chosen. Okay? So that's the end of the first part of topic 4.